Hi, in this video we will teach you about the cardiovascular system. In this chapter, we have the introduction to the cardiovascular system, types of blood circulatory system, control of heart rate, heart sound, regulation of blood flow, blood pressure, and the last one is conduction system of heart. Let's get started. What is cardiovascular system? The cardiovascular system can be thought of as the transport system of the body. This system has three main components, which is the heart, the blood vessel, and the blood itself. First is heart. Heart is the center of the blood circulatory system. It collects blood and pumps the blood through the circulatory system to all parts of the body. Second is blood vessel. Blood vessel composed of many branches. They transport blood from the heart to all parts of the body and then return the blood to the heart. There are three types of blood vessels, which is arteries, capillaries, and veins. Arteries transport oxygenated blood away from the heart. Usually, veins transport deoxygenated blood to the heart. Meanwhile, capillaries convey blood between the arteries and veins. And the third one is blood circulatory system. There are two types of blood circulatory system, which is pulmonary circulation and systematic circulation. The pulmonary circulation is the flow of the blood from the heart to the lungs and back to the heart again. The systematic circulation is the flow of blood through all the tissues in the body except heart and lung.
Let's look at the blood flow through the heart. The wall of heart is thick and made up of cardiac muscle. The heart has a double-walled sac called the pericardium surrounding it. The space between the heart and the pericardium is filled with fluid. It acts as a lubricant to reduce friction during a heartbeat. The heart is also covered with minute blood vessels. Let's follow the blood flow to understand what part does what. Let's look at the blood flow through the heart. The blue is representative of blood vessels containing deoxygenated blood, while the red blood vessels have oxygenated blood fresh from the lungs. The superior vena cava receives blood from the head, neck, upper limbs, and chest, while the inferior vena cava receives blood from the trunk, viscera, and lower limbs. Both superior and inferior vena cava end up in the right atrium, one of the four chambers of the heart. The heart has four valves. The purpose of the valve is to keep blood moving in the right direction and not flow backwards. Blood exits the right atrium through the tricuspid valve and enters the right ventricle. Blood exits through right ventricle through the pulmonary valve and enters the pulmonary artery. Again, it is an artery because blood is flowing away from the heart. The pulmonary artery then splits into the left and right pulmonary arteries, which go to each respective lung. In the lungs, gas exchange occurs. Blood discards carbon dioxide and picks up oxygen. It comes back from the lungs through the pulmonary veins, entering the left atrium. Then the blood is pumped into the left ventricle through the mitral or bicuspid valve. Finally, the oxygenated blood leaves the left ventricle through the aortic semilunar valve, entering the aortic arc. The aorta, which is the largest of all the arteries, distribute the oxygenated blood to the rest of the body. The aortic arc supplies the head, arms with blood. Then it curls downward from behind the heart, forming the descending aorta, which descends through the chest and continue down through the abdomen. What about the heartbeat? A heartbeat is a heart rhythmic contraction due to the flowing of blood through the heart. Heartbeat has two phases, diastole and systole. It is a recurrent beat throughout life. During a diastole, the muscles of the atria and ventricle relax. The blood flows into the ventricles. Mitral and tricuspid valves open, and semilunar valves close. During an atrial systole, muscles of both atrium and both ventricles relax. Again, the blood flows into ventricles. During a ventricular systole, muscles of both the ventricles contract. Blood flows into the pulmonary artery and aorta. The mitral and tricuspid valves close, and semilunar valves open. A heartbeat is composed of a diastole phase, then an atrial systole, a ventricular systole, and back to the diastole and repeat. Let's see how the heart sounds are forming. Heart sounds are due to the heart valves closing. There are two types of heart valves. First one is atrioventricular valve. It is found between the atria and the ventricles. Next one is semilunar valve, between ventricles and the pulmonary trunk in the aorta. First heart sound is due to the atrioventricular valves closing, and we call it lup. The second sound is due to the semilunar valves closing. And so when you hold the stethoscope go up to your heart and you are listening to your heartbeat, lup dup, lup dup, lup dup. And this is all due to the cusp of the valves slapping against one another while they are closing.
Now we're going to discuss about blood pressure, which is one of the subtopic in cardiovascular system. So now, what is blood pressure? Let's see the definition of the blood pressure. Blood pressure is defined as the lateral pressure exerted by flowing blood on the walls of the arteries. Types of blood pressure. There we have three types of blood pressure. The first one is arterial blood pressure, the second one is pulmonary artery blood pressure, and the last one is central venous pressure. Systolic pressure. Systolic pressure is the top number which measures the force of your heart exerts on the walls of your arteries each time it beats. The normal range of systolic pressure is 100 to 140 mm of mercury. Diastolic pressure. Diastolic pressure is the below number which is minimum pressure exerted by the blood on the artery wall when the ventricles relax. The normal range for the diastolic pressure is 60 to 90 mm of mercury. To get a clear picture of how actually it works, I come out with a diagram. So from this diagram, we can say that diastolic pressure occurs when the ventricle relax and systolic pressure occurs when the ventricles contract. This is a blood pressure chart. There we have 5 blood pressure ranges as stated below in the table. Let's see the problems of blood pressure. The first one is high BP, which is known as hypertension, and the second one is low BP, which is known as hypotension. This picture shows hypotension causes blood to flow slower, while hypertension causes thinner artery walls. Now, let's see what is mean airway pressure. Mean airway pressure is the average pressure exerted by the blood on the artery during the complete cycle of ventricles contracting and relaxing. The normal range of the mean airway pressure is 100 mm of mercury. Calculation of mean airway pressure. Let's see the formula for mean airway pressure. Mean airway pressure equals to 1/3 times pulse pressure plus diastolic pressure. Pulse pressure can be calculated by pulse pressure is equals to systolic pressure minus diastolic pressure. Factors that affect blood pressure. There we have 4 factors that affect blood pressure. The first one is peripheral resistance, the second one is viscosity, third one is blood volume, and the last one is cardiac output. So let's see the first one, peripheral resistance. Peripheral resistance is the friction of blood against blood vessel walls. Constriction of arterioles increase both resistance and blood pressure, while dilation of arterioles decrease both resistance and blood pressure. The next one is viscosity. Viscosity is thickness of blood. When the viscosity increases, the blood pressure also increases, while viscosity decreases, the blood pressure also decreases. Third factor that affecting blood pressure is blood volume. When the blood volume decreases, the blood pressure also decreases, while when the blood volume increases, the blood pressure also increases. The last one is cardiac output. What is cardiac output? Cardiac output is volume of blood pumped by heart in 1 minute. When the cardiac output increases, the blood pressure increases, while cardiac output decreases, the blood pressure also decreases. Let's continue with the electrical conducting system of the heart. What is cardiac conduction system? The cardiac conduction system is a collection of nodes and specialized conduction cells that initiate and coordinate contraction of the heart muscle. It consists of sinoatrial node, which is SA node, then atrioventricular node, AV node,
then atrioventricular bundle, also known as a bundle of His, then right and left bundle branches, and lastly Purkinje fiber. Okay, now what is the role of the SA node in conduction system of the heart? SA node functions as the pacemaker of the heart. It initiates the contraction of the heart. It also sets the rhythm for concentration of the heart. Then it produces action potential at the faster rate than other area of the heart. Following that, the action potential of the SA node act as a stimulus to adjacent areas of the heart. And lastly, when action potential originate in an area of the heart other than SA node, the result is called an ectopic beat. To get a clear picture of how actually electric conduct in our heart, I come out with the animated diagram which shows how it happens. First of all, action potential originate in the SA node and travel across the wall of the atrium from SA node to AV node. Then, action potential pass through the AV node and along the AV bundle, which extends from the AV node into the interventricular septum. Following that, AV bundle divides into right and left bundle branches, and action potential descend to the apex of each ventricles. Lastly, action potential are carried by the Purkinje fibers from the bundle branches to the ventricle walls.
We are going to discuss about the mechanism by which acetylcholine and adrenaline influence the activity of pacemaker fibers and thereby modulate heart rate. Normally, the heart beats at about 60 beats per minute, and the rate is directed by the activities of pacemaker fibers in the SA node. But as we know, the heart rate can be slowed down. And the heart rate can be speeded up. The principal idea is that the potassium channels work in opposition to the channels, that is when a channel is open due to the membrane hyperpolarization. The influx of positive charges carried by sodium leak out of the cell through the open potassium channels. Since the membrane depolarization depends upon intercellular accumulations of positive charges, the membrane potential does not depolarize until the potassium channels close. What is shown in this slide. When potassium channels begin to close, some of the positive current flowing through the H channels can depolarize the membrane. When more potassium channel close, more of the positive current flowing through the H channel depolarize the membrane. And when depolarization reaches threshold, the calcium channels open, which trigger the influx of positive charges and hence the obstruction of the pacemaker action potential. So, if the accumulations of positive charges through the H channels could somehow be speeded up, the depolarization would be faster and it would take less time to reach threshold as shown here by the red line. But if the accumulations of positive charges could somehow be slowed down, the depolarization would be slower and it would take a longer time to reach threshold as shown by the green line. The way that is accomplished is by modulating the numbers of open potassium channels by either keeping some open or keeping some closed. The modulations of potassium channels is accomplished with the neurotransmitters acetylcholine, which is released by the fibers of the parasympathetic nervous system that innervates the heart, and by adrenaline, which is released by both the adrenal gland and by the fibers of the sympathetic nervous system that innervates the heart. We begin with the control condition without any acetylcholine or without any adrenaline. The pacemaker fibers hyperpolarize as indicate both in the top trace of the membrane potential and in the lower drawing of the pacemaker fiber with the minus signs indicating hyperpolarization. The potassium channels are open, allowing for the efflux of positive charges, and the gates on the H channels have not yet opened. Next, the gates on the H channels opens and the positive charges float into the cell as the potassium channels close. The cell progressively depolarizes until threshold is reached, at which the point the potassium channels are all closed. This is the normal depolarization. When acetylcholine binds to the muscarine receptor, it makes those channels opening persistently. That is, the channel will not close even when the membrane is strongly depolarized. Now, when the gates on the H channel opened and there is an influx of the positive charges, it will take longer for the positive charges to depolarize the membrane. Because some of the potassium channels remain open and allow for the leakage of positive charges even as the other potassium channels closed, there is enough influx of positive charges to depolarize to the threshold, but it takes a longer period of time to reach threshold. To drive the point home, excessive amounts of acetylcholine can actually stop the heart. Such concentrations of acetylcholine never occur naturally but can be produced in lab. When the gates on the H channels open, many potassium channels are persistently opened by acetylcholine that the positive charge is entering through the H channels that just leak out. The membrane potential remains hyperpolarized and never reaches the threshold. We next turn to adrenaline. When adrenaline binds to the metabotrophic adrenergic receptor, it makes some potassium channels to close. In the H channels opening, there are fewer open potassium channels through which the positive current can leak out of the cell. In other words, positive charges can accumulate in the cell faster than when those potassium channels were open. The rapid accumulations of positive charges in the cell causes a faster depolarization, and then threshold has reached faster, thereby speeding up heart rate. Let's look at the heart rates. First, here is a normal heart rate. And now, a slower heart rate due to acetylcholine. It is because more potassium channels are open. They have been opened by acetylcholine. And then the faster heart rate due to adrenaline. And remember, adrenaline closes potassium channels. Therefore, there are fewer potassium channels that are open, and those are the reasons that the heart rate can be modulated by both acetylcholine and adrenaline.